Thank you very much, Yiannis. So I'm Nick, and I'm here to talk to you about fusion power, harnessing the power of the sun, but here on Earth for clean electricity production. So Yiannis and I started a company together, First Light Fusion. This is our mission statement, solving the problem of fusion power with the simplest machine possible. And what we're working on is a new approach to inertial fusion. It's one of the two main ways of doing it. And the core of inertial fusion, the very heart of the technology, is something called the fuel capsule. So this is one. It's a tiny millimeter-sized object, and it's filled with the fusion fuel, two different types of hydrogen. And the way inertial fusion works is you basically have to implode the fuel pellet at very, very high velocity. You basically squash it extremely quickly. And as you implode the fuel pellet, the volume of the fuel pellet is going down, so the density of the fuel is going up. That's one of the things you need for fusion. And if you do it quick enough, you can kind of overpower nature. Nature doesn't want to let you make this concentration of energy that you get in the fuel. It wants to cool everything down. So the way inertial fusion works is you basically overpower all of those processes with just really high velocity. Now, how do you make the fuel pellet implode? The established way of doing this is to use a high-energy laser. Basically, you shine the right laser on the right fuel pellet and it implodes at the right velocity. Great. But there's a problem with that. The laser is very complicated and very expensive, so it's not cost competitive for power production. This is where our approach comes in. We have a new way of doing it. And instead of using a laser, we use a high-velocity projectile. And the projectile comes and it hits into, well, it doesn't hit into the fuel capsule. That doesn't work very well. The fuel capsule needs to implode at hundreds of kilometers per second, but the projectiles that you can get to, they're only sort of tens of kilometers per second. And this is where the secret sauce comes in. So the secret sauce is the design of what we call the target. And the fuel capsule is part of the target, but it's not the whole thing. So the projectile comes in, and it hits this target. And the key technology we have is what we call the amplifier. The amplifier does two things. First, it shapes the shock waves which are produced on impact. What you want for inertial fusion is a spherical implosion of the fuel capsule. So we turn the one-sided impact into a spherical implosion with the amplifier. And the second thing the amplifier does, and this is what we call it, an amplifier, is it boosts the velocity. So the velocity that the fuel collapses at is not the same as the projectile velocity, it's much higher. And I've got a silly demo for you to try and show you, illustrate how that can work. So first, the basketball. Okay, not very exciting. Second, the tiny football. Also not very exciting. If I put the two together in just the right way, then I get a much higher velocity out. So what we've done there is we've stolen a bit of energy from the big, slow-moving, heavy thing, and we've put it into the little, small thing. Okay, but couldn't we do that again? Couldn't we do 3? So I do have 3. And I'm pretty nervous about doing this because it's quite hard. This is the first time I've done it on stage, so I'm going to try and do it. You can privately make a prediction about what's going to happen. Hitting me in the face with a tennis ball is a possible outcome. So if this works, give me a big cheer. Okay, so what about, couldn't I do 4? What about 100? Could I do 100? Well, no, probably not. But this links to something that's really important from the history of inertial fusion. There's a thought experiment. And you imagine if you have a big sphere and it's filled with gas, the fusion fuel, and you give it a tap on the outside simultaneously all around the whole outside. You're going to put a little vibration into that gas. You're going to launch a sound wave, which is going to travel into the gas. And it's going to move inwards. And as it moves inwards, it's going to strengthen because the area is always decreasing, so then the energy keeps kind of going up. Not the energy density keeps going up. And eventually it's going to turn into a shock wave, and then it'll keep moving towards the center, and it'll strengthen and turn into a really strong shock wave. And then at some point, it gets to the focal spot. And what happens there? Actually, the solution to the equations of fluid dynamics, at that point, is a singularity. The actual solution to Navier-Stokes equations is infinite temperature and infinite pressure and finite density. So, and this is really important in the history of inertial fusion. You see back in the old literature, they're using this antiquated language talking about infinite accumulations of energy. This is why the spherical implosion works well. How can this happen? This doesn't make any sense, right? How can these equations, which we know so well, produce an infinity? Actually, it turns out we really don't know the equations for fluid dynamics very well. So this is a screenshot from the Clay Institute's website. There's this problem to do with the Navier-Stokes equations. It's called the Navier-Stokes existence and smoothness problem. So if you could prove that Navier-Stokes equations always have a smooth solution with no infinities, you'd win $1 million. And I did think about the thing on the previous page. They have thought of that, so I'm not going to win $1 million for noticing the example on the previous page. So we don't really know these equations very well. What am I on about? I've gone on this massive mathematical tangent here, so let me go back. That converging shock solution, there's two things, at least two things, which stop you from getting that infinite temperature. The first thing, sorry, Yiannis, but it's not all about fluid dynamics. If you add a tiny amount of heat conduction into that problem, then the infinity goes away. The heat conduction stops the singularity from forming. And the second thing is you can never be perfectly spherical. So any deviation that you have at the start just gets magnified as the focusing takes place. So it never gets to that perfect singular point, and you never get that infinite temperature. Okay, going back further still, right, to what we were talking about before, we use a high-velocity projectile, and the thing we've been obsessing about, or one of the things we've been obsessing about over the last 6 months, is the tilt on the projectile and how that affects the performance of the amplifier and the fuel capsule. And actually, we've been developing a method of measuring the tilt of the projectile on impact, which sounds like it's an easy problem, but this is one of our projectiles. It's got a piece of copper in the front, which is 30 millimeters across, which you can see there. On impact, this has the same kinetic energy as a family car going at about 100 miles an hour, so it's quite a dynamic environment. We can measure the projectile tilt now to 0.1 of a degree, which is very easy to say, and I wanted to show what that actually looks like. So we can tell to smaller than the width of a human hair how flat we're hitting the target. The point I want to kind of get to with this is what we're trying to do is we're trying to find a robust new approach where it works anyway, even given all the imperfections of reality. And I also want to make a point about revolutions, because that's the theme of the event. So first things first, yeah, fusion power will be a revolution. Right, obviously. The revolution I want to highlight for all the students here is one which has been going on for a long while, but is still very much going on, and that's the use of simulation tools to design technology. We've been designing aircraft for decades using CFD simulations. At first light, we're using them to discover and invent a completely new approach to, as Yiannis put it, one of the hardest problems out there. If you, as young engineers, if you can master what that means, if you can understand that the mathematical reality, the equations, that's one thing, and then the simulated reality, the model in the computer, that's another thing, different thing, and then the actual reality is a third thing, different from both of those. If you can understand that, then you can make these tools your own, and you can do incredible things with them. Thank you.